So today is October 13th and you're here for Econ 249. What you're looking at on the screen is the prize in economic sciences that's awarded by the Royal Swedish Academy of Sciences, the Nobel Prize in Economic Sciences. So if you've been following it, they announced on Friday, I think, the Nobel Peace Prize. Does anyone know who received the Nobel Peace Prize for this year? No? Okay, so it was awarded to the World Food Program. It's a subsidiary of the United Nations, and it's because of the work that they did during the pandemic, the World Food Program. But that's not what you're looking at here. This is the prize in economic sciences. So the Nobel Prize is given in many different areas. The Peace Prize is one area. There's chemistry, physics, and there's also economics. And this was announced on the 12th of October, yesterday. And it was awarded to two professors, Milgram and Wilson. They're professors at Stanford University. And it's because of their work, proven work that they did about auctions. And auctions, as you know, has been around for generations. But there's a specific auction theory that came about in the 1960s, and they built on that. And auctions are of many different types. There's open auctions, closed auctions, but there's two, I guess, auctions that are followed in the world, and that's the English auction and the Dutch auction. And traditionally, auction theory has focused on tangible items. The work that they did focuses on items that are not tangible. So like radio waves, frequency waves, internet, things like that. So it's quite interesting. You can read up on it on your own. But what I found is fascinating is they were able to obviously receive a gold medal for this, and they actually win a dollar amount. So they receive a prize of 10 million Swedish kroner, which is approximately a little over $1 million. So it's like a lifetime of work, but it's not really the money. It's to be recognized by the Royal Swedish Academy, by the Alfred Nobel, in memory of Alfred Nobel. Okay, so that's our little bit of information for today. It's quite significant in the field of economics, so you should be aware of what's going on. But we're going to start with a new chapter today, and that's chapter 7. So we just finished chapter 6, and we're going to start chapter 7. But before I do chapter 7, I'm going to put a whiteboard here. I'm going to start with a story. Okay, so I see some of you have just joined. The story is about two students, and these two students were taking statistics as a course. And the day of the exam, they were late. So in fact, they were so late that they missed the exam. They didn't make it in time. And they didn't make it in time because they were out the previous night partying and they couldn't wake up in time to take the test. So they arrived to campus late and they couldn't take the test. But the two of them approached the professor and said, we're really, really sorry we couldn't take the test because we traveled together and we got a flat tire on our way to campus. Is there any way that you can please give us a makeup test? So this professor, just like me in my syllabus, the policy is no makeup exams. But this professor was gracious enough to say, okay, I will give you a makeup test on one condition, that you take the test in two separate rooms. These students were ecstatic. They said, great, wonderful, of course, we'll take the test in two separate rooms. Thank you for giving us a makeup test. So on the day of the makeup test, they arrived on time, and the professor put them in two separate rooms with their question sheets. Each of them had only two questions on the test. First question was on the first page, and the question had something to do with the material that they studied, something to do with statistics, right? The material. And that question was worth 5 points. The second sheet had the second question. That question was worth 95 points. And the question asked, which tire was the flat tire? Okay, so we're going to pretend that you were one of those two students. Okay, and if we were in the classroom, I would ask you not to discuss this with your neighbor. You would have to write down on a piece of paper which tire was the flat tire. So now, since we're not in the classroom, we're here online, I'm going to do a poll, and you're going to have to select the answer choices. So I'm going to type it in a moment. Don't put your answer choices in the chat box because it's not going to work. Okay, so make sure you put your answer choices in the poll that I show you in a moment. So let me type it up. Okay, so in a car, there are 4 tires, right? It could be the left front, left rear, right front, right rear. So which tire do you think was the flat tire? So just pick one, and I'll give you a few minutes. So I'm not supposed to see your answers. That's why when we do it in the classroom, it's sort of by secret ballot, and we collect all the ballots. I have one student collecting, another student writing it on the board, reading it out. So the whole process takes about 15 minutes usually in class, but of course this is much faster. So I'll give you a few more minutes. So I'm not going to be able to read it. You just have to pick which tire was the flat tire, and then I'll discuss it. Okay. You have another minute to answer the question. So you have to choose one. Okay, and I'm going to stop. Okay, 30 seconds. Pick a tire. Okay, everyone picked a tire, and I'm stopping now. Okay, so usually when I do this, I try to predict which tire is the one that most students pick. And you can see here that most students picked right front tire. I've been doing this for many years, and I'm going to say 99% of the time, right front is the most popular choice. There's actually a reason behind this. There was a psychological study that proved that the brain tends to pick right front in anything. So if you walk into a room and you see a group of people, you tend to gravitate towards right front. If you had to choose something on a plate, and you had to, so you select something on a plate, you tend to look at top right. So this is not something that I came up with. This is something that, let me take a picture of this before we reach this because I need these answers. Okay, so the reason why most people choose this is because our brain tends to function this way. It might be a right brain, left brain thing. If you happen to choose left rear, there's nothing wrong with you. It doesn't mean that there's something wrong with your brain. Okay, it's just that you don't tend to think like right front. That's all it means. There's nothing wrong with you. So a couple of questions here. I don't know if it's an English versus US thing. It's a worldwide thing. So this study, it proves that all people actually think right front, even if the question was based in England. So I'm going to take those values and now we're going to calculate probabilities with that. Okay, so I'm going to share my Excel screen. And again, nothing wrong with you if you did not choose right front. So going back to my story, it's actually a legendary story. It's not exactly true. It didn't happen to me, but you know, be careful when you lie. Okay, so let me open Excel first. Okay, so here we have our answer choices, and I'm going to look at the results that we just had. So we had 16 chose left front. We had 15 choose left rear, 23 and 13. Okay, so if I can go back to the screen. Okay, any questions for me before I start? Because I won't be able to go back and forth. So let's go back to my Excel sheet. Okay, so this is what the polling showed. So now I'm going to say that the correct, whatever correct means is, the correct response is right front. So in other words, the one that most students responded is right front. Right? So that's how I'm choosing this as the success, the correct response. So now I have to figure out if this is a binomial distribution. So why do I need to know? I need to know what's the probability that 0 students would pick right front. So in this class, if I'm considering this class to be participants in the experiment, how many students would pick, or would it be 0 students? What's the probability of 0 students picking right front? What's the probability that all students would pick right front? What's the probability that 5 students would pick right front? So that's the goal in this little exercise now. Remember, with binomial distribution, we have to make sure it satisfies all the properties, which means this is a Bernoulli trial. And so that's what we're going to do now. First, n. The value for n is my sample size, the number of students in my class. So that means I need the sum of this. So it's showing me that there are 67 students in the class. P is my proportion of success. Now, what do you think P is? It's not probability. So it's a proportion of success. You're getting success out of how many outcomes? So I'm saying I'm getting 1 success out of 4 outcomes. 1 success out of 4 outcomes. So 1 out of 4. Right front is my success. And it's a success because that's the one I'm interested in. I'm saying that's the one that's most popular. So, and again, why did we choose right front? Because there are studies that show that, because it shows in our poll here that most students picked right front. Okay, so this is 0.25 or 1 out of 4. X is my number of successes. So X stands for number of successes. In other words, X stands for the number of students who chose right front. So it's the number of students who chose right front. So it could be 0 students who chose right front, 1 student, 2 students, 3 students, 4 students. When should I stop? How far should I go?
23. Well, to 67.
67, right? Yep. There are 67 students, so I'm going to go up to 67. Okay, so we have that. Now, if it's a binomial distribution, I need to make sure it satisfies all the properties of the Bernoulli trial, which it does because they're independent of each other. So that's why I said if you were in the classroom, you cannot collaborate and discuss your answer because you would influence each other. So in this way, you couldn't discuss it. You had to decide on an answer choice and submit it. So it satisfies all that, and each answer will have a success or a failure. Either it's right front or it's not right front. Okay, so it's definitely a binomial distribution. So that means I can start typing the formula for binomial distribution, which is equal binom dist x, comma, and n is 67, p is 0.25, and then I type the word false. And I type false because I want the probability when x is equal to 0. If I type true, I'm going to get the probability for everything less than the value of x and everything, the sum of everything below x. Okay, so this is my formula and I hit enter. What is this telling me? It's telling me the probability is 4.257 times 10 to the negative 9, which means I take this decimal point and move it 9 times to the left, which means the probability that no student picks right front is 0. It's a 0 probability that nobody will pick that. Okay, so if I copy and drag this all the way down, now I have all the probabilities for all the students. And if I want to know the probability when all 67 students choose right front, that probability is also 0. 0 probability that all will choose right front. So I can ask many questions, right? What's the probability that probability that at least one student will pick right front? At least one and more than one. The minimum is 1. So that means I have to add up the probabilities from 1 all the way down. Or I can do 1 minus the probability when x is equal to 0. Okay, so you need to know that. What if I asked you for the mean? Now with binomial distribution, the mean is n times p. So I can actually calculate that. Mean n is 67 times proportion is 0.25. So that means the average number of students who would pick right front is 16. About 16 students in this class will pick right front. So that kind of makes sense here because if I see the probability is showing me that the probability that 16 students pick right front is about 11%. Okay. So again, the other thing you learn for binomial distribution is standard deviation. So you can plug that formula in n times p times 1 minus p. Okay, so this is just an example of how you could apply the binomial distribution. Again, you're applying it to, you could apply to anything, right? As long as it satisfies the Bernoulli trial. And it's quite simple. It answers the question, and it doesn't always have to be at when p is equal to 0.5. Any questions for me? No questions? Okay, so let's stop sharing here. And let's go back to chapter 7. Okay, so chapter 7 is a new chapter. And a couple of questions here. Priscilla, you asked me could you repeat when we choose true or false in the formula? Okay, so in the binomial distribution formula, you use false when you want the probability for that exact value of x. So always use false. Okay, that's just the easiest way to do it. Always use false because you want the probability when x is equal to that particular value. If you type true, it's probability when x is equal to that value plus everything below the value of x. So it's more complicated to do that. Before I start chapter 7, I'm going to mention that Excel number 3 is due a week from today. Okay, so a week from today is Tuesday, October 20th. So you have to go back to your groups and work together to complete Excel 3. I just emailed each of you through Blackboard with the Excel assignment. If you never received it, if you never received my email, it's because your email address that is listed on Blackboard is incorrect. You need to fix that. You need to send an email to IT to get them to fix it. So again, same way, you work together, put your answers on a Word document and upload it on Blackboard. Make sure you only include the names of the people who participated, who communicated, and who did work. Okay? If you never heard from anyone, you do not have to put their name in the Excel assignment. So again, you have a week from today. I sent you an email. If you never received the email, contact your teammates. Okay, any questions for me? Okay. So chapter 7 is continuing with probability distribution. So in the last chapter, we spent some time talking about general probability distributions. And then I focused on discrete probability distributions. And I said that there were 4 kinds, and we spent most time on binomial and Poisson. Now this chapter 7 is going to switch to continuous probability distribution. And there's 3 types. There's the normal distribution, the uniform distribution, and the exponential distribution. So continuous probability distributions is exactly what you may think it is. All the values of x are continuous data. Now it gets a bit more complicated because x is a value that is not just 0, 1, 2, 3, but it's a decimal or a fraction. And then you're going to calculate probabilities associated with x. The normal distribution is the only distribution you will study for continuous probability distributions in this course. For the same reason that the uniform is really simple and the exponential is quite complex. Okay, so let's look at what exactly a continuous random variable is. It's a variable that can assume any value on a continuum. That means it can assume an uncountable number of values. So meaning it's not just 0, 1, 2, 3, and so on. It's 0, it's 0.009, it's 0.111, 0.125, 0.338, 0.999, and 1, and so on. So it's really uncountable, right? When you think about it, how many decimal places are you talking about? But it's interesting that a continuous random variable can be applied to the thickness of an item, the time required to complete a task, the temperature of a solution, or height in inches. So let's look at each of these, right? If I'm talking about the thickness of an item, I'm saying you're measuring an item, and you can be really precise when you measure it. So you have down to the decimal, the second decimal with inches, and so on. how long it takes to complete a task. Again, very precise measurement. If I talk about height measured in inches, again, with a decimal or a fraction, precisely. So these can potentially take on any value depending only on the ability to measure accurately. So I'm going to start with an experiment, and not an experiment, an example. We had enough experiments. The example is, let's say you're a website designer. So you design websites. And let's say that you did something to the website recently, and you want to know now, like you added a few things, you took out a few things. So now you want to know, has that changed how long it takes to download the web page? That's important information, right? So you need to know that as a website designer, how long it takes to download a web page. So let's say you have some data from before that you can compare it with. Let's say last month, when you didn't do anything to the web page, you had the average time it took to download a web page. So now I'm going to move to a blank screen so I can write stuff on it. Okay, so let's say last month you found out that the mean time to download a web page was 7 seconds. Okay, I'm just making that number up. I don't know if it's a high number or a low number. And you also were able to calculate the population standard deviation from last month based on last month's data, and that was 1 second. Okay, so this information you already know. And now this month you added a few things, you took a few things away, and you want to know, did that change? So you collected data, you timed how long it took to download the web page. You did this at different times of the day. You did this on different days, weekdays, weekends. You collected all that data and you put it into a histogram. So let's say X is the time, how long it took to download the web page. And let's say the y-axis is your frequency. So let's say that it took, so the frequency is quite high. So I'm looking up here. Many times the web page downloaded at 7 seconds. Okay, many times. And then this is the rest of the data. So the data is showing that infrequently, so hardly, it took a long time to download. So it took a long time to download, and sometimes it was extremely fast, less time to download. So you ended up with a shape like this. Now, if I had to draw on the top of this graph, it would end up being like this. So it gives me something like a bell-shaped curve. Okay, now if we calculate the standard deviation, we see that the mean ends up being, or because you did some things, you found out that the mean did not change from last month, so it didn't really affect it. And let's say that the population standard deviation also stayed the same, nothing changed. Okay, so now I'm going to do a few markings here. So if the center is 7, this is going to be the mean plus 1 standard deviation. This is going to be the mean plus 2 standard deviations. Mean plus 3 standard deviations. This is the mean minus 1 standard deviation, and so on. Okay, so this value here will be 8 seconds. What is this value here? 9, okay. and then we have 10. So this value here is 7 seconds, 6, and 5. Okay, so this is still 7. So I'm basically drawing the mean and I'm adding my standard deviations to it. Any questions so far? Okay, so we have 7, 8, 9, 10, 7, 6, 5 to the left. So why did I stop at 5 seconds and why did I stop at 10 seconds? Because I can see here that anything beyond 10 seconds and anything less than 5 seconds hardly ever happens. Frequency is so low, it hardly ever happens. So I could disregard it. I'm going to say that we're not interested in anything beyond 10 seconds and anything less than 5 seconds. So this shape is interesting. This shape is actually leading me to a normal distribution. And now I can see that I can, okay, that's the question here. Shouldn't the left side be 4, 5, and 6? Yes, thank you for that. It should be 4, 5, and 6, right? Yes, I'm missing the 7 here. Thank you for that. So please correct that. So that's 4, 5, 6, 7, 8, 9, 10. Okay. So nothing beyond 4 seconds, less than 4 seconds, nothing beyond 10 seconds. So this shape is interesting because what if I was not talking about website page downloads and instead I was talking about thickness of an item? And let's say I asked all of you to measure your pencil, the thickness of your pencil, the thickness of your pencil. So I'm going to say that most of you, so again, frequency is high, so most of you are going to come up with a value that is similar. Very few will have a value that is extremely high, so very thick pencil, and very few will have a very thin pencil. So most of you will end up with these values, and then if we plot it into a histogram like this, we'll end up with the same curve. What if I asked you to look at baking temperatures? So most items are baked at a temperature that is, let's say, 350 degrees. Most things are baked at 350 degrees. Very, very rarely, almost never, will you bake something at 600 degrees. Almost never will you bake something at 100 degrees or 50 degrees. So again, if you plot that, you're going to end up with a curve like this. So what's interesting is, going back to our slides, any experiment, any example that you're working on, whether it's website page download or height measured in inches, they're all going to end up with a curve like this. So that's interesting. If almost all experiments or phenomena or disciplines or industries end up with data that gives you a shape like this, then why not use some kind of a model where we all base our applications, our calculations on that model? So that's what mathematicians did. And they came up with the normal distribution model. So that's why the normal distribution is the most commonly used and most widely used probability distribution. And it's the most important one. So you really need to understand this. Okay, so this is the normal distribution model. And when I say normal, it does not mean usual, it means regular. Okay, this is like the standard. So that's why it's called normal. So this slide is important because it has all the properties of the normal distribution. When you have your homework questions, you will be asked to refer to properties, and this is where you'll find it. Okay, so the model for symmetric bell-shaped unimodal histograms is called the normal model. So the first property is that it's bell-shaped and symmetrical. Okay, so you saw in my drawing, and you can see in the graph here that the shape has a bell shape to it, and it's symmetric. And now the second property, and you know this because when you are dealing with a symmetric histogram, the mean is equal to the median is equal to the mode. Okay, so the center of your bell-shaped curve is the mean, and that center is mu. Okay, so we have that here, that center is mu. Now if I mark my standard deviations, so this would be mu plus 1 sigma, mu plus 2 sigma, mu plus 3 sigma. Those are my standard deviations. So this would be 1 standard deviation, 2 standard deviations, 3 standard deviations. This would be -1 standard deviation, -2 standard deviations, and -3 standard deviations. Okay, so the third property is saying that range is approximately equal to 6 standard deviations. So the range is from -3 sigma to +3 sigma. So range is approximately equal to 6 standard deviations. Now why approximate? Because we know that the curve goes on beyond 3 standard deviations to the right and the left. It can go on forever, right? There's no ending to that value for x because x is my x-axis here. X can be any value on a continuum. So, but it's so minute that we can disregard anything beyond 3 standard deviations. So that's why we say it's approximately 6 standard deviations, 3 to the left, 3 to the right. Okay, and the fourth property is this stuff in the red, and I'm going to rewrite it. X is the range for x is from -infinity up to +infinity. So x is less than +infinity and greater than -infinity. So that means this value x on the x-axis can range from -infinity to +infinity. So these are the properties that you're looking at. Now, one thing to note, this y-axis is not exactly frequency. The y-axis is the probability density function. So it's a probability. It's not frequency anymore. Okay. Questions for me? Okay. Moving on. What are the conditions necessary to use a normal model? Now, again, this question is asked in your homework, so you need to be aware where to look or where to find it in your slides. Again, all these slides, if you don't know, are available on my Stat Lab under Course Tools Document Sharing. Okay, so you need to know when you can use a normal model. I said it's very commonly used. You can apply it to many different disciplines, but you have to be aware that these 3 conditions have to be met. The first condition is randomization. So randomization is the sampling method has to be at least not biased, and the sample has to be representative of the population. So 2 things have to happen for randomization. Your sample or your sampling method cannot be biased, and the sample must represent the population. So that's why when I gave you the website homepage download time, I said that the data was collected at different times on different days, so you're not biased by collecting data on a particular day, particular time. Okay, so you have to meet randomization. Second thing is 10% condition. And this is not talked about much because it's usually assumed that the sample must be no larger than 10% of the population. You're not going to have a sample that is more than 10% of the population. Samples are usually small, but it should not be larger than 10% of the population. Third condition, success-failure condition. That is n times p and n times 1 minus p have to be at least 10 to satisfy the success failure condition. So you have to check these two conditions, np and n times 1 minus p. It has to be less than at least 10, less than or equal to 10, which means 10 or greater, so that you can continue with the normal distribution. Okay, so those are the three conditions. So now we're looking at three curves, and the only differences in the curves are the value for mean and sigma. This is mean and this is sigma. So mean is the center of the curve, and sigma tells you how it varies. So I'm going to ask a question. Let's pretend that these three curves are three different mutual funds. And let's say you have some extra money and you want to invest in these in one mutual fund. Which mutual fund would you pick and why? Now, there is no right or wrong answer. I want you to explain to me why you would pick a certain mutual fund. Okay, three different mutual funds. Only thing you know about them is the mean and the standard deviation. Why would you pick one that you choose? And give me your explanation.
I would choose the pink mutual fund
Okay.
because I see it more stable than taking a high risk on like a yellow one.
Okay. Does anyone want to agree or disagree with Naya? So it's okay to disagree. Yan, you say you agree?
I was
Gilbert?
going to say the blue one seems like a better option because it's more, I don't know, it looks like more predictability, looks like a good range of,
Okay,
I don't know,
so
it
you
just looks
and
better.
okay, so you and Karina say the same thing. You would pick the blue because it seems to be evenly distributed. Okay, I'm going to go back to what Nayang said. You're slightly off with your explanation. It doesn't mean that you shouldn't choose pink or you should choose pink. Let me explain what you're looking at first, and then maybe you might choose a different answer. So the center of the blue curve is right there, and that's the mean. The center of the yellow curve is also there, and that's the mean. The center of the pink curve is here. Okay, so the center is my mean, and if these are mutual funds, then maybe it's the mean, the average, the expected value. Maybe it's expected returns. Okay, so if these are expected returns, which return is higher? Out of the three curves, which expected value is higher? The mean, the average. Out of the three, if I look on the x-axis, Oscar is right, the pink one is higher. So looking on the x-axis, right, the pink value is higher. It's a higher expected return. So now what's the difference in the curves? Now let's look at the standard deviation. The yellow curve is quite narrow. The yellow curve is telling me that the standard deviation is smaller than the blue curve. The yellow curve is telling me that the expected value doesn't deviate as much from the returns don't deviate as much from the center because the standard deviation is smaller. The yellow curve is less risky. The blue curve is a little bit more risky because it's more spread out. So that means the values, the observations are a bit further from the center. My pink curve is telling me, although I will have a higher expected return, the highest expected return, it deviates a lot. So I could get a lot more or a lot less. And the standard deviation is the highest. Nayang, do you want to change your answer now?
Mm,
So you originally said you chose the pink because it's less risky, right? But now, okay. Now that can't really make sense because we see it's so spread out. It's very, very risky. The pink curve is the most risky. So if you want less risky, you would choose the yellow curve. So again, there's no right or wrong answer. You just need to be able to explain why you would choose something. Okay. Any questions for me? So seems like all you need really is mean and standard deviation to look at a curve. And that's the beauty of the normal distribution. That's really all you need, the mean and the standard deviation. So mean will shift the distribution to the left or the right. The standard deviation will increase or decrease the spread. So that's how you get your shape. But remember now, this is your x on the x-axis, and this is not frequency. It's a probability density function. So that's probability. So you're looking at a normal distribution, and it just depends on these two parameters, mu and standard deviation. So now when I did the binomial distribution with you, I gave you the formula for binomial probability distribution. It was this long factorial formula, and I said we won't use it, we are going to use Excel. So I showed you the formula in Excel. In the same way, I have to show you the formula for normal probability distribution. And that formula is this. And when you first look at it, it might not look complicated, but it is quite complicated because you can see here the exponent. We know pi, we know e is a constant, but the exponent, it's raised to a negative 1 divided by 2, x minus mu, and then remember x is a decimal, so it can get super complicated. So we're not going to use this formula, and you don't need to memorize it. In fact, mathematicians thought about this, and they said that since the normal distribution is so applicable across all disciplines and all these experiments and phenomena, and it's very easy to draw. Only things you need is a mean and a standard deviation. Why don't we standardize this into one model so that everyone can use that standard model, apply it to their experiment or their phenomena, and then get the answer that they're looking for. So it doesn't matter if you're talking about website download times or thickness of an item. Let's all use a standard model and then apply it to each of our cases. So this leads us to this idea of z values and z scores. So the standard deviation is what we're going to use as a ruler. So Judah, your question is that formula in Excel? The normal distribution formula is in Excel. It's not the formula that I just showed you. It's slightly different. We'll get to that later. But first, I want to mention that we're going to think about what I just said, right? So these mathematicians said, let's transform what we're using right now, our x units. So everybody has different x units, depends on what the experiment is. Let's transform it into a standard. Let's call it z units. So any normal distribution with any value for mean and any value for standard deviation combination can be transformed into the standardized normal distribution. So you can transform x into z. So your first thing really is transforming x units into z units. So this way we can have a standard way to compare values. And that formula is really simple. In order to get z units, you take your value for x minus mu divided by sigma. So all you need is the expected value, that population mean for your experiment, and the population standard deviation. Then you got your z units. And once you have your z-score or your z-value, we're saying that the mean for the z-score is 0, and the standard deviation for the z-score is always going to be 1. So mean will always be 0, and sigma will always be 1. So once you translate x into z, it's really quite simple. And I want to mention that let me show you the properties of the standardized normal distribution. So it's the same thing, nothing really has changed. The properties of now the standardized z distribution or standardized normal distribution is this. The first property stays the same. It's bell-shaped and symmetric, same as you saw before, right? No change. Bell-shaped and symmetric. The second property is that the mean is equal to 0. So that we know, right? So that here mean is equal to 0. The center is your mean. The mean is always equal to 0, and the standard deviation is always equal to 1. That's the next property. If the standard deviation is always equal to 1, then I can say this is 1, 2, 3. And this is -1, -2, -3. Because remember, standard deviation is equal to 1. So we have 0 in the center, 1, 2, 3, and -1, -2, -3. Okay, next property is that the area under the curve is always equal to 1. So this is important. I'm saying all this area under the curve, the entire area under the curve, that entire area is equal to 1. How is that equal to 1? Well, remember, this is your probability density function. So if I add up all my probabilities for all the values of z, probabilities, total is equal to 1, or 100%. So the area under the curve is equal to 1. And then we have the range for z. Actually, I'm jumping a little, but let me put it in here. Z ranges from -3, it could be equal to as well. Z ranges from -3 to 3. So you can see here the range of z is from -3 to 3. This is my z axis. The value for z ranges from -3 to 3. Again, why are we only stopping at 3? Why not -4 to 4 or -5 to 5? Because anything beyond 3 standard deviations is so minute and minimal, the probability is almost 0. It will almost never happen. So we can disregard anything beyond 3. So that's why we stop at 3. Which means then range is equal to 6 standard deviation, and standard deviation is equal to 6, then range is equal to 6. So with the standardized normal distribution, range is equal to 6. Any questions for me? So this chapter is quite theoretical. It's just a matter of understanding these concepts, and then we'll slowly start applying it. Okay. No questions? Okay, moving on. So this is something that is called the empirical rule. Okay, so I'm bringing this up now because I know I said that I have to transform x into z before I apply the normal distribution, or before I start calculating probabilities for the normal distribution. However, without transforming x into z, so without transforming x into z, I can use this rule called the empirical rule, which has been proven by mathematicians. And it's also called the 68, 95, 99.7% rule. So what does this rule say? It says that it doesn't matter what your experiment is, whatever you're doing, or whatever you're working on, once you collect data, 68% of all your data will fall within one standard deviation. That's quite significant. They have actually proven this. And it's valid for any situation across the board, as long as it has the properties of a normal distribution. So what does it say? It says 68% of all your data will fall within one standard deviation. Then the rule says that 95% of all your data will fall within two standard deviations. And then finally, 99% of all your data will fall within three standard deviations. So 100% minus 99.7% is very minimal, so we can disregard anything beyond three standard deviations. Okay, so without transforming x into z, you can still calculate probabilities. So that's what we're going to do now in the last few minutes of class. Calculate probability. Can you turn your microphone on? I think we're getting some disturbance. We're going to calculate probability using empirical rule. Okay, so it's also called the 68, 95, 99.7% rule. So here's our example, and we're going to do a poll. And the question says, the graduate management admission test, the GMAT test, has scores from 200 to 800. Scores are supposed to follow a distribution that is roughly unimodal and symmetric and is designed to have an overall mean of 500 and a standard deviation of 100. In any one year, the mean and standard deviation may differ from these target values by a small amount, but we can use these values as good overall approximations. Okay, so a lot going on here. The GMAT has scores ranging from 200 to 800. You're told that it's symmetric and unimodal, meaning it's a normal distribution model. You're given the mean, because you need the mean, and you're given the standard deviation. Those are the two parameters that you need when you're discussing the normal distribution. So the manager says, a new applicant to our company earned a 600 on the GMAT. Where does she stand among all those who took the GMAT? Okay, so I'm going to type in the answer choices, and then you're going to give me the answer and explain it to me. Oh, you could be wrong, Judah. Let's see. Okay, so 600 on the GMAT means you did better than how many who took the test. Okay, so I'm going to help you by writing the empirical rule on the top. So it's a 68, 95, 99.7% rule. And if you had to draw this curve, but the center is mean. You were given the mean of, let's say, 500. Okay, so I'll write that up here too. Mean is 500. Sigma is 100. Okay, so now you know 1 standard deviation, 2, 3, 1, 2, 3. So this would be 600, 700, 800. This would be 400, 300, 200. So now the question says this applicant has a 600 as her GMAT score, and she did better than how many people who took the test. Okay. So I'll give you a few minutes and then we'll work on it together. So to answer Chris, your question is when do we use z-score? So right now we don't need to use the z-score because, and I'll explain why. Right, I'll explain why after we do the poll. Because right now you can just apply the empirical rule and get the answer. You don't need to transform x to z. And so we will be using the z-score a little later on, but not in this particular example. Okay, I'm going to stop the poll here. Okay, stopping here. See. Okay, so I think most of you followed Judah's lead. So I'm going to ask someone else to explain to me why you chose 84%. So let's move on to the next slide because it gives us a nice clean slide here. And I'm changing the settings so that you can write on this. Okay, so who wants to explain why? Let me fix that. The answer choices were 34%, 16%, 84%, and 95%. So I'll start marking this up. So I also said we're going to use the empirical rule, 68, 95, 99.7% rule. Okay, so this is my center, which is mu. That's my 500. So we have 600, 700, 800, and all the way down to 200. Okay, so the empirical rule tells me that 68% of all my data falls within one standard deviation. So that's one standard deviation. 68% of all my data falls within one standard deviation. The manager, according to the example, wants to know how well a score of 600 is. So if somebody scored 600, that person did better than how many people who took the test? What percentage of people? So the manager wants to know all this from 200 all the way to 600 did better than how many? Okay, so we said that this is a normal distribution. It's a bell-shaped symmetric curve. If it's symmetric, then if I draw this line in the center, then I can figure out from negative infinity all the way to the center, what's my percentage? From negative infinity up to the center, what's my percentage? Jonathan says 50%, and I agree. So it's exactly half, right? It's symmetric, so 50%. The entire area under the curve is equal to 100%. So half of that is going to be 50%. So now if I'm interested in from negative infinity all the way up to here at 600, then you're right. I would just do this area would be half of my 68. And Karina, you're right. It would be 34%, right? So I'm looking at just half of this from here to here. It's the half of that 68. So that's 68 divided by 2, that's 34%. So that means my answer is 50 plus 34, 34%. Okay, questions for me? So you could have done this in different ways. You just need to recognize that you can apply the empirical rule and get the answer. So to go back to the question that was asked, Christopher, why aren't we using the z-score at this point? Because I don't need to. At 600, it's exactly on one standard deviation. If somebody came with an application form and said that their GMAT score was 629, now it gets a little complicated. I can't exactly use the empirical rule. I would have to transform my X 629 unit value into a z-score. So that we're going to do in the next class, where we're transforming X into Z, getting the probability and coming back and applying it to the particular example. Okay, make sure you do your homework. Chapter 7 homework is open. You can start doing it. If you don't understand everything, then it probably means that I haven't completed the topic for chapter 7. But remember, chapter 6, the homework is due this weekend. So don't forget to complete it. Okay. Any questions for me before I end class today? You're welcome. So I'm going to stop recording.